Hi students, my name is Nitesh. Shet. I am from Manara. So last class we discussed about the topic from 10th standard, that is circles. In circles we already discussed about what is meant by circles, what are the parameters we have in that circles, and also we discussed about theorem 10.1. So let us move on to the next theorem, that is theorem 10.2, that completely based on tangents. Before going to theorem 10.2, so we have to discuss about number of tangents we can draw on the circles. So let us move on to the next topic. So here we have to know about how many tangents will be drawn for the circle, inside the circle and on the circle and outside the circle, from outside the circle. So how many tangents will be drawn, we have to discuss here. So here there are three cases are there. So firstly I will take any point inside the circle, and in the second case I will take a point on the circle, and in the third case I will take one point from outside the circle. So if from the use of those points, so we have to draw a tangent. So on passing through that point, so we have to draw a tangent here. So firstly we have to discuss about the first case, that is inside the circle, that is point inside the circle. That is first one. Point inside the circle. Inside the circle. Yes. So here I will take any point inside the circle here. Here I will take the point here. So this is the point. So passing through this point, here I have to draw a tangent. Whether it is possible? No, it is not possible. But here we can draw a point. It becomes a secant. So there is no any case of tangents. So here we can draw some lines here. Just over here I will draw a line. So and here I will draw a line. It's passing through this point. So I can draw infinite number of lines, but no one it is tangent. No one it is tangent here. So that's why no tangent is available here. So that is, so no tangent, no any tangent, no any tangent to the circle passing through the point lying inside the circle, lying inside the circle. Yes. So in first case the point is inside the circle, so that's why there is no any tangent will be drawn when the point is inside the circle. Yes. So let us move on to the second case. In second case we have to take a point on the circle, on the perimeter of the circle. The second case is point on the circle. Point on the circle. Yes. So on the perimeter you can take any point here. So here I will take the point here. So passing through this point we have to draw a tangent. So here just observe how many tangents will be drawn here. So here only one tangent it is available. Only one tangent is drawn lying passing through this point. So when a point on the circle we can draw only one tangent. That is only one tangent. Only one tangent to the circle passing through the point lying on the circle. So in this case there is no any tangents because the point is lying inside the circle. Here only one tangent will be drawn. So the point is lying on the circle. And the next case we have to take a point outside the circle. Outside the circle we have to take any point here. So let us take the third case. It is point lying outside the circle. Lying outside the circle. Yes. So here we have to take any point outside the circle. Here I will take the point here. Then passing through this point we have to draw a tangent. Yes. So here I will take the point here in this side. Firstly I will take the above the center of the circle. I will draw a tangent here. So yes, here I will draw a tangent passing through this point. Here it is one possibility. And so secondly, below the center I will draw, we can draw another tangent here. Yes. So here, so another tangent we can draw here. Yes. So that means here only two tangents can be drawn when a point is lying outside the circle. So there is two tangents to the circle passing through the point lying outside the circle. Yes. So here there are three possibilities are there. So firstly it is when a point is lying inside the circle, there is no any tangent can be drawn here in this case. And when a point is lying out on the circle, there is only one tangent can be drawn. Only one tangent will be drawn here. So there is no any other tangents is possible in this case. Yes. In the third case, when a point is lying outside the circle, then we can draw two tangents. One is the above the center of the circle, and another one is the below the center of the circle. So we can draw this case. And on the circle we can draw infinite number of tangents. There is infinite number of points are there on the perimeter. Infinite number of points are there. Using all those points we can draw infinite number of tangents. But from a single point we can draw only one tangent here. So here one tangent. When we take this point, here one tangent can be drawn, and when we take this point, we can draw only one tangent here. So from a single point on the circle, lying on the circle, so we can draw only one tangent. When a point inside the circle, there is no any tangent there, it is not possible. And when we have point outside the circle, whatever the cases we have, so when a point is outside the circle, so we can draw only two tangents. One is above the circle, center of the circle, and another is below the center of the circle. So these are the three cases. It's very important. So also here in this case, we have to take the theorem 10.2. In that case, so we want this case. So we have to take this case for the proof of theorem 10.2. So let us take the theorem 10.2. Yes, so we already discussed about the number of tangents drawn to a circle from some points. So in that the last case it's very useful for us for the theorem 10.2 here. So theorem 10.2 is based on that case only. We have to draw a tangents from a point lying outside the circle. So the theorem 10.2 states is that the length of tangents drawn from an external point to a circle. The length of the tangent we have to take. The length of tangent drawn from an external point to a circle are equal. We have to take. So let us take the theorem 10.2. So theorem 10.2 here. It is the length of tangents. The length of tangents drawn from an external point to a circle are equal. Yes. So we have to prove that one. That means, so whatever the number of tangents, only two tangents is available, only two tangents it is possible. But in that, when we draw two tangents from an outside of the point outside of a circle, so those two tangents are equal. So the length, when we measure the length of those two tangents, those two are equal. So we have to prove here. So for that we want a circle and a point outside the circle, and we have to draw a tangent. So here I will take the point here. Here I will take this as A, and the center of the circle I will take O. Then from the point A I will draw two tangents here. One is above the center of the circle here. One is above the center of the circle, and another one is below the center of the circle. Yes, here it is like this. Yes. Then I will join this point. That means it is an intersecting point, and take it as P, and this is an intersecting point, I will take it as Q, and we have to join this OP here, and OQ we have to draw. Also we discussed about the intersecting point with the circle. It's a perpendicular. So we already learned that one. So this makes a 90 degree, and this makes also a 90 degree. Also I will join, here I will join OA. So with the center I will join this point. Yes. So here just observe we have two triangles. So with the help of these two triangles we have to prove that PA is equal to PQ. AQ we have to prove. AP is equal to AQ we have to prove here. So firstly we have to start with the given terms. Given. So what are the given terms here? Here O is the center of the circle, and P and Q are the intersecting points with tangent drawn, and AP and AQ are the tangents here. So O is the center of the circle. O is the center of the circle. It is given, and AP and AQ are tangents drawn to the circle. Tangents drawn to the circle from an external point. A. Yes. So this is the given term, that is a circle it is given, and we have a point A lying outside the circle, and from the line A we drawn two tangents here, that is one is the AP and then AQ intersected the circle at P and Q respectively. We know that one. So what we have to prove here? So here we have to prove the length of tangents are equal when we draw two tangents from the outside of the circle. So here we have to prove AP is equal to AQ. AP is equal to AQ we have to prove here. So whether in need of construction, here we constructed those things here. So apart from the length of the tangents and apart from the external point, we drawn something here, which is OP we drawn, and OQ and OA. Join OA, OP and OQ. That is construction. OP. Join OP, OQ and OA. Yes. So then we have to prove. Yes, there are two methods are there for proving these things. So here one is the right angle is possible. So from in the right angle triangle we can insert Pythagoras theorem also. Another one possibility is taking the congruency. Taking the congruency, that means in 9th standard we already discussed that one. In 9th standard we already discussed that is, so in that we have to use some congruence rules. So I will solve by both the methods. So only one method you have to refer. So two methods are there, you have to refer only one method, it is enough. So firstly I will take the triangle method, that is congruence rule method. So first, so let us prove. Yes, here we have to take two triangles. Firstly we have to consider two triangles. One is the AOP and AOQ. Consider triangle AOP and triangle AOQ. In that we have to look at this and what are the similarities are there. So here, just observe, here it makes a 90 degree. So this angle makes a 90 degree. So already we learned that when a tangent is drawn, then when compared to the radius of the circle, so those two are making the 90 degree. That is, it's a perpendicular. So from theorem 10.1, we already discussed that OP is the smallest distance. That one is perpendicular. OP is perpendicular to AP, we already discussed. So that's why here also making 90 degree, and here also it makes the 90 degree. That is, it's a right angle, it's also a right angle. We know that one. That is, here we have to take those things. So that is angle APO is equal to angle AQO is equal to 90 degree. So from theorem 10.1, so 10.1 we learned that angle APO is equal to angle AQ is equal to 90 degree. Then any other equalities? So radius will be always equal. Anywhere we have radius means it's always equal. That is, OP is equal to OQ. OP is equal to OQ because it is radius of circle. Radius of circle. Then come just observe those two triangles. So OA is the common side for both the triangles. That is, OA is equal to OA. So this is common side. This is common side. Common side. So that means here we have three similarities, three equalities. So here in triangles we learned about only similarities. Similarity means A similarity. Their corresponding sides are proportional. But here just observe these two triangles are looking like one and the same. Completely the same. That's why we have to take the congruency. Congruency means completely equal. Sides also equal, angles also equal. So all the corresponding sides are with the length, compared to the length, equal. So that's why we can take triangle AOP. Triangle AOP is congruent to, so this is the congruency. Triangle AOQ here. So because of from SAS congruence rule. Because of from SAS congruence rule. Congruence rule. So this is also very easiest method. Then when we have two congruent triangles, their corresponding parts of congruent triangles are equal. So that means we can take AP is equal to AQ. AP is equal to also AQ. Then other triangle, this angle is also equal to this angle, and this angle is also equal to this angle. Those are the corresponding parts. So that's why we can take it as equal only. So this is about the one of the method we can use. So this is on the CPCT. Therefore, the length of the tangents drawn from the external point to the circle are equal. So we have the conclusion here. So this we solved using the congruence rule. Congruency, from the help of congruency we proved this thing. So another method is there. So you have to refer only one method. So here another method is the Pythagoras theorem method. So we have to start from the beginning. So let us take the Pythagoras theorem method. So let us take the another method here. Here we have to take the right angle triangle and we have to apply the Pythagoras theorem here. So here already we know that there are two right angle triangles are there here. So particularly in each right angle triangle we have to apply the Pythagoras theorem. So let us take the triangle. So in triangle AOP, so it's a right angle triangle, right angle at P. So that's why apply Pythagoras theorem here. So here, which one is the hypotenuse here? The side opposite to the right angle, we have to take it as a hypotenuse. That is AO square. AO square is equal to AP square plus OP square. OP square, because it is Pythagoras theorem. Pythagoras theorem. Yes. Then here we have, I will take this as equation number 1. Then let us take the triangle AOQ. In triangle AOQ, so we can insert the Pythagoras theorem. The side opposite to the right angle is hypotenuse. That's why we can take AO square is equal to AQ square plus OQ square. So because it is Pythagoras theorem, from Pythagoras theorem we get this equation. Yes, I will take this as equation number 2. From equation 1 and 2, just observe the LHS side is same for both two equations. That's why the things which are equal to the same things are equal to one another. So that's why from equation 1 and 2, so we can equate AO square A square. In the LHS side we have A square means the RHS must be equal. That is AP square plus OP square is equal to AQ square plus OQ square, because AO square is equal to AO square. Here we have this relation, so that's why we can write this one. Yes, so here just observe OP is there, OQ is there. The radius is always same. So that's why we can cancel out easily. So also we can take any one. OQ can be expressed in the form of OP also. Let us take that one. AP square plus OP square is equal to AQ square plus OP square, because OP is equal to OQ, so that is radius of the circle, radius of circle. So only one radius means we have a radius. So 2 or 3 means we can take radii. Yes, so let us take. Then OP square and OP square getting cancel. When we transpose such thing, any one of the OP square means here it becomes minus AP square, OP square, OP square getting cancels. So remaining it is AP square is equal to AQ square. Taking square root, when we take the square root, so AP is equal to AQ we have. So that means length of the tangents drawn from the external point. We have two tangents. Those two tangents are the length with the measure of length. So those two are equal we have. So this is the theorem 10.2. There are two methods are there. So triangle, with the help of triangles, congruence rules, we can solve this that one, and also with the help of Pythagoras theorem also we can solve this one. So you have to write only one method in the examination. Okay, so let us move on to some problems. So let us take the first problem of this video here. So here we have a two concentric circle. Two concentric circle means we have two circles having only one center. So here it is center O is common for C1 and C2, and which touches the smaller circle, that is chord of the larger circle. Here we draw a chord here, here we draw a chord here for the C1 which touches the circle bisected at the point of contact. That means here this AB, I will take this as AB. This AB is the chord for C1 and tangent for smaller circle C2. So that means when we take a perpendicular distance, when we take a line segment from O, so it's a perpendicular. We have a perpendicular, that means OP is perpendicular to AB. So when it is perpendicular, so center, the line segment which bisected from the center to the chord, it bisects into two parts. So that one we have to prove, that is AP. So I will take this as P, and so AP is equal to PB we have to prove here. So firstly we have to write given. So what are the given terms here? So given is the C1 and C2 are the two concentric circles having center O. C1 and C2 are two concentric circles having common center O. So this is the thing we have. Then what we have to prove here? So here we have to prove AP is equal to PB, and here let us take AB is the chord. AB is the chord drawn to the larger circle and touches the smaller circle at one point. Yes, so we have this thing, and then we want a construction, that is we have to draw join OP. So it must be, so when it becomes AB is the tangent to the circle, this circle C2, so that it becomes a perpendicular only. So we already learned in the theorem 10.1. So let us take what we have to prove here. To prove, that is AP is equal to PB we have to prove. AP is equal to PB we have to prove. So here there is another method also that we can prove here. So here we can draw a triangle here, so it's also possible. When we draw a triangle here, so then here this side is common, and this is the 90 degree we have, but here these two are the radius, it is also formed, but it is not needed, because when we draw a line from the center of the circle to the chord, it bisects into two other parts. We already know that one. So that one is also possible here. So let us take the proof. Yes. So let us take the proof here. So here, when we draw a line from this circle to the chord, it bisects into two other parts. So here already we know that AP is perpendicular to AB. So here AB is the chord touches the smaller circle here. So then here OP is perpendicular to AB. So therefore OP bisects the chord into two equal parts, that is OP bisects, therefore OP bisects the chord drawn to the larger circle. Therefore AP is equal to PB we can prove. So it is the proof. So from the which method? So here we have to take, it's only the method. So that is we already taken that from the geometrical point of view. That is, so always, so when we draw a chord here, for a circle, when we chord is drawn to the circle, when we take a line segment from the center. When we take a line segment from the center, so it must, so when it is perpendicular, only when it is perpendicular, then only it bisects into two equal parts, because we know that OP is perpendicular to AB, and it becomes that AB is the tangent. AB, it looks like the tangent of this smaller circle. So another thing is there, another proof is also there, so we can use. So let us move on to the another method here. So let us take another method here, and also you can draw. For that, here we have to join. Here we have to join OP, OA and OB. OA and OB. When we join OA and OB here, yes, here I will join OA and OB here. Yes, so these are the two radius. So that's why we have to consider OPA and OPB triangle. So in triangle OPA and triangle OPB, in these two triangles we have to look at the congruence rule. So we have to take the equalities. What are the equalities we have? So here OA is equal to OB because radius of the circle. OA is equal to OB because it's a radii of circle. Then OP is common for both the two triangles, that is OP is equal to OP. So this is the another method of proof. This is the another method. So we can prove these things from the help of congruence also. Here OP is equal to OP, so because it is common side. Then another equality is, so OP is perpendicular to AB, we already know that one, so that's why we have to take these things. That is, those two right angles, that is, these two angles are 90 degrees. That is angle OPA is equal to angle OPB is equal to 90 degrees. When we have these things, we can take that one. Then, so from these three things, we have SAS congruence rule. So from SAS congruence rule, we can take triangle OPA is congruent to triangle OPB. That is, triangle OPA is congruent to triangle OPB. So when we have those two triangles are congruent, then we can take AP is equal to PB as a corresponding parts of congruent triangle. That is, therefore AP is equal to PB because it is CP/CT for those two triangles. That is, corresponding parts of congruent triangles. These two are equal here. So this is also we can prove. So this is another method. So that one method is also useful for us, and this method is also useful for us. But here the confusion is, so here it becomes, so when we have a chord for the first larger circle, so it also touches the circle. It also touches the second circle, smaller circle. That means it touches at one point means, it becomes a tangent. So obviously the center, the line segment from the center of the circle, it bisects this means, so we can take this as a perpendicular here. So OP is perpendicular to AB, we can take. So let us take some of the homework. Let us take one homework here. Here it's related to the last problem we discussed. That is, here also we have two concentric circles are of radius 5 cm and 3 cm. That means here we have this. It is a radius of first circle, that is 5 cm, and 3 cm is radius of small circle, that 3 cm is. So here we have to find the chord of the larger circle which touches the smaller circle. That means here just observe, we have these two sides. Means from the right angle triangle we have to insert the Pythagoras theorem here. From that we can calculate AP. So after that we can take the same length as PB. That's why already we learned that these two are equal length. So that's why after that we have to add those things. Then we get the result, that is the complete chord AB. So try to solve that problem. Also, those who are watching this video for the first time, please subscribe our channel and don't forget to press the bell icon. You can get the notification very easily. Also hit the like button. Thank you and all. Be safe and stay home. Thank you.